You know, we spend so much of our lives clicking, typing, and swiping, but have you ever just stopped and wondered what's really going on inside your computer? Well, today we're going to peel back the layers. We're going on a journey from your screen deep into the silicon heart of the machine to see how it actually thinks.
I mean, think about it. It's something you probably do 100 times a day without a second thought. But that simple double click, it kicks off this incredible super high-speed chain reaction. Now, it might seem like magic, but it's really just a series of very logical steps. So let's dive in and peel back that first layer. Okay, so our journey starts in the most familiar place, the world of software. This is the universe of apps and programs we all use every single day. But here's the thing. It's not just one big mess of programs. It's actually built in very distinct and very crucial layers. Basically, you can split all software into two main camps. First up, you've got system software. The best way to think about this is like the foundation of a house. It's your operating system, right? The core stuff that manages all the hardware. And then you have application software. This is the house that's built right on top of that foundation. Your web browser, your games, your word processor, all the tools you use for specific tasks.
And this relationship is absolutely crucial. See, the system software, with the operating system right at its core, provides all the essential services that your application software needs to run. A program like your word processor doesn't actually talk directly to your hard drive. No way. It has to ask the operating system to do it for it. And right there, that's our first big clue. Each layer in this whole system hides the complexity of the one below it.
Right, so what is all this software made of anyway? Well, if you look underneath these slick icons and windows, it's all built from code, just a massive set of instructions. But it's not just a simple to-do list, not at all. It's packed with logic that actually lets the computer make decisions. So, the brain inside any program is something we call control statements. These are the bits of the code that direct the flow of everything. They allow a program to react differently depending on the situation. It's kind of like a choose-your-own-adventure book, but for the computer. A control statement looks at a condition and says, okay, if this thing is true, go do this. But if it's false, go do that instead.
Let's take a super simple example. Imagine a program needs to check if you're old enough to enter. The code first checks a condition. Is the user's age greater than 18? If the answer is yes, it follows one path and shows access granted. But if the answer is no, that else part kicks in, and it follows a completely different path to show access denied. And that simple little decision, that if this, then that, is a fundamental building block for pretty much every single program you use.
Okay, so we've got our code, it's full of all this clever logic, but we've hit a snag. A big one, actually. A computer's processor, its brain, doesn't understand programming languages like C or Python or Java. It just doesn't speak that language. So how do our human-readable instructions get turned into something the machine can actually run? Well, that's where translation comes in. A translator is this special kind of program that acts like, well, a bridge. Its one and only job is to take the source code that a human programmer wrote and convert it into the super low-level machine code that the computer's central processing unit, the CPU, can directly understand and act on.
And there are basically two main ways this translation can happen. You can think of a compiler like a book translator. It reads the entire program first, translates the whole thing at once, and then spits out a brand new super fast file that can run on its own. An interpreter, on the other hand, is more like a live translator at a conference. It translates and runs the program one line at a time. Now, it's a bit slower, but it's way more flexible for things like testing and debugging.
All right, so once our code gets translated, we have finally reached the bottom layer of software. We're at the native language of the machine itself. This is what the hardware truly understands, and you might be surprised by how simple it is.
Seriously, after all those layers of incredible complexity, the apps, the code, the logic, the translators, it all comes down to just two things, two simple signals. And that is binary, the language of zeros and ones. And look, this isn't just some abstract math concept. It is physically tied to the hardware. A 1 can represent an electrical circuit that's on, and a 0 represents a circuit that's off. Every single piece of information on your computer, this explainer, your photos, your music, is ultimately just stored and processed as these gigantic sequences of ons and offs.
You can see here how our normal, everyday numbers have a direct translation into binary. The number 2 becomes 010. The number 7 becomes 111. It's really just a different way of representing the exact same value, but it's a way that is perfectly suited for an electronic machine that can only think in terms of on and off.
Okay, so we've got this language of zeros and ones, but where does the magic actually happen? Where do all these signals get processed? For that, we have to look inside the physical hardware, the silicon brain of the machine itself.
Believe it or not, this simple diagram you're looking at is the basic blueprint for pretty much every computer out there, from massive data servers all the way down to the smartphone in your pocket. It shows the fundamental organization that brings all of those zeros and ones to life.
The key thing to understand here is the flow of data. Let's go all the way back to our original double click. That click is an input. That command gets sent to the memory to be held for a moment. From there, the CPU, the central brain, grabs that instruction and does all the necessary calculations. And finally, the result gets sent to an output unit, like your screen, and boom, the app window appears. That whole loop, input, memory, processing, output, happens in a blink of an eye. It's incredible.
So what's the big secret? How does all of this complexity actually work so smoothly? It's this incredibly powerful idea called abstraction. Each layer we've just looked at, the application, the code, the binary, the hardware, it hides the complexity of the layer below it. This lets us build these unbelievably powerful systems, all starting from simple on-off switches.
When you get right down to it, it all comes back to this simple idea. Software is a set of instructions or commands that tell a computer what to do. That is it. Every complex program you've ever used is just a set of commands, translated down through all those layers of abstraction until they become simple on-off signals telling the hardware exactly what to do.
You know, if you look at the history of computing, from giant vacuum tubes to the microprocessors we have today, each new generation was really defined by adding new layers of abstraction that made the machines more powerful and way easier for us to use. So, that leads us to a final, really fascinating question. As technology keeps evolving, what do you think? What will that next incredible layer of abstraction be?